In Chapter 11, we're going to start looking at the normal distribution, and we'll stick with this idea of the normal distribution throughout the rest of this particular semester. Now, when we talk about the normal distribution, the first thing we'll do is we'll look at some characteristics of the normal distribution. Then we'll look at the 68, 95, 99, 7 rule, which is also called the empirical rule. You'll see it referred to as either, this longer name with the numbers or the empirical rule. And then we'll start to look at the standard normal distribution. And the standard normal distribution is so important because we use it to find probabilities and some tables. And the standard normal distribution uses the random variable z. We'll start learning how to use the normal tables that I handed out in class. And then we'll also look at how we can work with the normal tables working backward. And then this assumption of normality, how is it met, or how can we verify that it's met? Because again, a lot of times we assume normality, but how do we check to make sure a distribution is actually normal? So to get started here, you're going to need a couple things. First of all, you'll need your tables that I handed out in class, and you'll also need a calculator. So let's go ahead and start by looking at some characteristics of the normal distribution. So to begin with, the normal distribution is also called the Gaussian curve or the Gauss curve. And basically, it's any curve or a family of curves that has this nice little bell shape here. So here would be an example of a normal distribution that's more flat. This one is a normal distribution that's more peaked. Sometimes it's referred to as a bell-shaped curve. Now there's two very important variables that define a normal distribution, and those variables are mean, and since it's based on a population value, it's the Greek letter mu, so again, this is population mean. And then, of course, the standard deviation, sigma, Greek letter again, so we know that this is a population standard deviation. And these two pieces of information define what the curve looks like. It talks about where it's located, so this value of mu gives it its measure of central tendency. So this gives us its measure of central tendency or location. And the standard deviation gives us some information about the spread of the curve. So we can see this curve on the left has quite a bit more spread, and so its standard deviation would be larger than the curve on the right. Now both of these curves are centered at the Greek letter mu. Now this function that you see here is the function that describes this curve. If we plugged in some value of x on the curve, let's say right here, if we plug that in here, I would get the height back out. I would get this value back out. Now if this was a calculus-based statistics course, what we would do is we would take this curve and we would work with it in terms of integration to try and come up with the areas underneath the curve. But we're going to not worry about this function. We're not going to memorize it. We won't work with it. We'll work with some tables instead. Now this value right here that we call the inflection point on either curve, the distance from the mean plus 1 standard deviation or the mean minus 1 standard deviation, this is the same distance over here, this is called an inflection point, and that defines basically what 1 standard deviation is at this particular inflection point. Now an inflection point means when the curve starts to change. So if you were thinking about skiing down this particular curve from up here down, that would be the part or the very point where it started to kind of level out. So our concavity here, and this is not a big deal to know this, but our concavity goes from from positive to negative back to positive again for any normal distribution, and that's the distance of 1 standard deviation. Now normal curves are used to model a lot of different things. We're going to focus more on the biological variables that we can use for modeling data, but a lot of data is shaped following this normal curve. Now it's usually not so exact as these curves, but it's usually pretty darn close. And then we'll see eventually that even if data isn't normal, I can normalize it. And even if it's skewed data, I can still normalize it by using some sampling techniques. So again, it's very important to understand a couple things. First of all, this is the normal distribution. The area underneath this curve is 1. So the area under the curve is 1. So this relates to, curve is 1. This relates to that idea of the complement. We talked about the total area underneath the curve has to be 1. when we were talking about the rectangles. Now the total area underneath this curve has to be 1, and that kind of goes along with the idea of the sum of the probabilities has to be 1. So this is one huge, very important characteristic of the normal curve. Also, a normal distribution is a continuous distribution. Some of the distributions that we've looked at before were discrete. So this is a continuous distribution. It's based on continuous random variables, RVSs, continuous random variables. And again, to define it, I need my mean. That gives me my center or my level of location, my position of location. And then I need my value for sigma to tell me how spread out the curve is and how flat it is. The next thing that we're going to want to look at are comparing different values of mu and different values of sigma. So for this particular graph, what we're doing here is we're comparing these three curves. I have a blue, a green, and a red curve here. And if you notice, they're all centered right here. We scope right down here at 15. So here, mu equals 15. Now, they're all at the same mean, but they all have a different spread. The blue curve has the least amount of spread, so it would have the smallest standard deviation. So this would be the blue curve. The green curve also has a little more spread than the blue curve, but not quite as much as the red. So this would be our standard deviation for the green, and of course the one with the most spread here is the red curve. So again, all of these curves have the same the same mean and different standard deviation. So they have the same location, its centers are all at 15, but they have different amounts of spread. Now we also can see here on this particular graph that these are all identical. If I were to slide these over, one would fit directly on top of the other. They're all spread out the exact same amount, but what changes here are their measure of location or their mean. So again, up here the standard deviations were different, here the means are different. So if we come down from the peak here, that kind of gives me an idea of where my mean is. It looks like it's right about 10. So this would be my blue curve. 15 straight down from here would be my green curve. And straight down here from 20 would be the red curve. So I can have curves that have the same standard deviation but a different mean and vice versa. Now there's an entire family of curves. There's an infinite number of these curves because every time I change their mean or their standard deviation, it produces a new curve. Also, as an interesting characteristic, notice these are perfectly symmetric. So symmetry is another nice characteristic of the normal curve. They're symmetric, and they're symmetric about the mean. Now because they're symmetric, that implies that the mean is equal to the median for a normal curve or for a normal distribution. So it's symmetric, and because it's symmetric, the mean and the median are equal. Let's go ahead and look at some graphs and try and come up with how we have these normal curves. Where do they come from? Well, they actually come from a discrete random variable, and if you can look here, you can see that this is a histogram based on a discrete random variable, because when we report height, and this could be the height of a particular gender, this is not male and female mixed together because we'd probably have two peaks, it'd be a bimodal distribution, but this is looking at heights. When we report heights, we usually report to the nearest inch, and then if I kept closing those gaps and went to the nearest half inch, quarter inch, eighth inch, etc., these blocks would start to fill in, and when I model it or smooth it with this curve, it has this normal shape. Now it looks like the middle or the mean of this distribution is somewhere right around here, 63.5, 64, around in that area. So we can see here that human heights, and again this is a particular gender, is modeled pretty closely with this nice normal curve. Now down here, this particular graph is right skewed. Now a normal graph, this nice smooth normal curve, is symmetric. So some data or some situations are well represented by the normal curve, others are skewed. So this right skewed curve is not represented by a normal curve at all. And what this is survival time in days of guinea pigs after they've been inoculated with a pathogen. So it looks like the majority of guinea pigs die within 200 days of inoculation, and then we have a few that survive out past that. But this is definitely a right skewed type of distribution, and a normal model would not be a good assumption to make here. Now when we start talking about the 68, 95, 99, 7 rule, we're talking about how area and therefore probability is distributed about the mean. So every single normal curve has the same properties or will hold for this rule, and again, another name for this rule is the empirical rule. And you'll see it referred to both ways. So all normal curves, as soon as they're defined for their mean and their standard deviation, will follow this rule. Well, the 68% part means 68% of all the observations will lie within one standard deviation of the mean. Now, within one standard deviation of the mean means one above and one below. So the particular distribution that we're looking at here, it looks to have a mean of 0. And we call this the standard normal random variable. And here we'll say Z is distributed normal, N is its shape, normal, with its mean of 0 and its standard deviation of 1. Now, whenever you see that it's written, whatever the first value is understood to be the mean. The second value is always understood to be the standard deviation. So again, Z is our standard normal random variable. And this is terminology that we'll use a lot, standard normal random variable. So if I take the mean and I add 1, because 1 is my standard deviation, and I subtract 1, 68% of the data will lie in this particular interval right here. And then if I add 2 standard deviations and subtract 2, that'll be 95% of the data will lie here. And then if we go out 3 standard deviations below and 3 above of the mean, 99.7% of the data points will lie within that particular interval. And we're going to be using this idea of the 68, 95, 99, 7 rule quite a bit. So this is definitely one that you will want to know and be able to use. Now what about if we weren't interested in 68 or 95% of the data? What if we were interested in figuring out something like 75% of the data? What proportion of the data would I be looking at then? Well, what ends up happening is I have to talk about a different number of standard deviations. So what if I wanted to say what percent of the data lie within a half a standard deviation of the mean? Well, you might be able to use symmetry and split this in half and say something like 34%, but what we really should do is try and come up with a rule that will help us determine how to work with other percentages from the data set. Let's go ahead and look at an example that uses this idea of the 68, 95, 99, 7 rule. This example is based on WHO, the World Health Organization, definition of osteoporosis, and it's based on a standardized bone density levels. So what we're looking at here, and again, this happens a lot. Sometimes you're considered normal, above normal, below normal. So we're talking about distribution here. So what's going on here is every single person who has a bone density level test done, their value is standardized, and we'll get into how to standardize variables in a little bit. But basically they're standardized and then they're compared to this curve. And so what ends up happening here is if you have a score that's no more than 1 standard deviation above or below the mean, then you're considered to have normal bone density. Now, if you have bone density that is between 1 and 2.5 standard deviations below the adult mean, and so that would be down here, so this would be between 1 and negative 2.5, so that would be this area right here, you're considered to have low bone mass. Now, if you have any bone density in this particular region, out in this direction, you're considered to have osteoporosis. So that's the medical definition of osteoporosis. If your bone density is 2.5 standard deviations or more below the young adult mean, then you are diagnosed with osteoporosis. So what we would want to do is we'd want to look at this and try and figure out, okay, what percent of young adults have osteoporosis? Well, in order to do that, we'd have to have some data to work with. So that's the next thing we'll look at, is a particular data set. So in this particular curve, we have 2 distributions that we're looking at. We're looking at women in the blue curve who are considered to be young adults. So the blue curve is young adults, and the orange curve are older women aged 70 to 79. Now notice here, young adults, normal 0, 1. And this doesn't mean their bone density is 0. What this means is their standardized score is 0. So again, this is the mean, and this is the standard deviation. This is the mean, and this is the standard deviation. So it clearly shows that as women age, their typical or average bone density moves from a standard score and drops. And in this case, it drops to a -2 for the orange curve. So again, women age 70 to 79 would not fit this blue curve because they have a different set of data that they follow. Now from here we could look and determine other probabilities as well. So for instance, we could look at finding the probability that a randomly chosen woman in her 70s has osteoporosis, and that means you're more than 1 standard deviation below the mean. So the way that we could look at this is we could focus in on this orange curve. So if we focus in on this orange curve, I'm trying to look at the area that's less than -1 on this particular scale. So here's -1 that we're looking at here, and I'm trying to find this area then that I have shaded. Now if I can find area that's shaded, what ends up happening is this is related to probability. So I'm going to use W to represent my variable for the women, so to make sure I'm using the orange curve for women. So I'm looking at the probability that my women's typical score is less than -1. Okay, so we can use our empirical rule, and the empirical rule would come up here and say, okay, within 1 standard deviation of the mean, and that would be right here, 68% of the data will lie within 1 standard deviation of the mean. The mean is -2, the standard deviation is 1, so that would mean 1 up and 1 down. And this value would equal 68%. So what I have here is 68% shaded in the green. So this would be 0.68. But I can see that in this tail area, I'm also going to have to come up with a little bit more area to work with. So I need to find this area as well to add with that to have the total probability. Well, because my curve is symmetric, I can use that property, and I have 68% of the data here. That means I have about 32% in this left tail, and I also have another 32%, or sorry, 32% total distributed between this left tail and this right tail. So that would tell me, because of symmetry, I can split that difference and I can add that together, and I would get here that about 84% of women in their 70s have osteoporosis. So again, 84%. Now how did that work again? This orange curve, I'm not even looking at the blue curve now because I'm talking about women aged 70 to 79. I find the mean, and then if I look at 1 standard deviation above and 1 standard deviation below, and here's my standard deviation, 68% of the data will lie in this green region. Well, 100% of the area has to be shown under the curve. So if I take 100% minus 68%, I'm left with 32%. And because of symmetry, the area below and the area above is the same. So this area right here is the same as well, 0.16. But I'm only looking for the area to the left and below, so that's why I add the 16%. So 84%, I'll make that look a little better. About 84% of women in their 70s can be diagnosed as osteoporosis using this definition on the standard scale. So all of this works because whatever their value was on the test, that value was standardized. And so that's what we like to do, is we like to take all these curves with different means and different standard deviations, and we like to standardize them so I can use one particular curve, one particular table to compare them against. And that kind of gives us a point of comparison. So let's go ahead and look at how we standardize the normal distribution. Well, basically what we do is we follow a formula, and this is the formula that we use to standardize a score. So definitely know this formula. memorize it. Now this formula will update a little bit as we go along and get some more information, but for now what we do is we call this a Z-score. And the reason we call this Z-score is every single score that we get from a data set, let's say every single possible height of women, I would take it and I would subtract the overall mean of women and divide by the standard deviation, and that would normalize that particular data. So again, if X is distributed normal with some mean and some standard deviation, what we do is we take each of these values of X and I subtract the mean and divide by sigma, and I turn this into the standard normal random variable, which has a mean of 0 and a standard deviation of 1. And this is definitely going to be important to know. So what we do here is this particular distribution that we have on the left is the heights of all women. Now the average height is 64.5 inches, and the standard deviation is 2.5 inches. But what if I wanted to compare, let's say, a woman's height to a man's height comparatively to their population that they come from? Well, the only way to do that would be to talk about how much taller or how much shorter they are than the typical person in their population. And the one way we can do that is by standardizing the scores. So for this particular example, I still have 68% of the data lie within one standard deviation of the mean, but on the upper end that would go to 67 inches down to 62 inches. But when I standardize or normalize it, it will go from -1 to 1, and there's no units here because it's standardized. It's a standardized height, it's not in inches, it's just a standardized number. So again, when you standardize a normal distribution, you change it so the mean is 0 and the standard deviation is 1. Any normal distribution can be standardized using this formula that we have right here. So now that we have this formula, let's go ahead and talk about what it means and how to interpret values that come from the formula. So we're looking at standardized scores. Now again, this is called a Z-score. And to get a Z-score, you take your observation, you subtract the mean from which the population came from, and divide by the standard deviation of the population. Now when you standardize, you should get a value that's probably not very big. It could be, well, it could be any number, but typically they're between, let's say, -4 and +4 for the most part. Because remember, 99.7% of the data lie within 3 standard deviations of the mean. So if we got a number like 4, that would mean we were way out in the tails of the distribution. So when X is 1 standard deviation larger than the mean, then what happens is the Z-score is 1. So this says I'm 1 standard deviation, it's positive, so I know I'm above the mean. So if I'm 1 standard deviation of the mean above the mean, that's mu plus sigma. So my Z value must have been, or sorry, my X value must have been mu plus sigma. And when I subtract the mean, the sigmas cancel, and I get a Z value equal to 1. Now when I'm 2 standard deviations larger, that would come from right here, the mean plus 2 sigma, what ends up happening here is I go through and standardize, and I get a Z value of Z equal 2. Now be careful when you're using Z's and 2's. A lot of times what ends up happening is they get kind of confused, so make sure your 2's look like 2's and your Z's look like Z's. Now when X is larger than the mean, then our Z value will be positive, and when X is smaller than the mean, the Z value of course will be below the mean, so it will be negative. So those are some important characteristics to remember while we're working on these, so that way when you calculate something you can look at it and say, okay, does this number even make sense? Let's go ahead and look at a particular value of standardizing scores. Now for this particular value, we're using the same data set as before, and women's heights, and I'm going to say W for women's heights are distributed normal with a mean of 64.5 inches and a standard deviation of 2.5 inches. Now the question I want to ask here is what % of women are shorter than 67 inches tall? And this would be important to know, let's say if you were a clothes manufacturer, so you could get, the clothes produced in the correct sizes to fit the majority of women. So what we're looking at here then is a curve. And for this particular curve, this is a curve with a mean of 64.5 inches and a standard deviation of 2.5 inches. So again, we are looking at the probability that a woman distribution that we have here, the women's distribution that we have here, that a randomly selected woman, or what percentage of women, are shorter than 67 inches tall. So women's heights less than 67. Okay, so if we come up here and find 67, I'm above the mean. That would be, I am looking for this particular area right here. So this is this shaded area. Now, because this is a symmetric distribution and this is the mean and the median are the same, 50% of the area is to the left. So I already know that. What I want to do is to figure out what this region is between the mean and the one standard deviation above, and then add it to the 0.5. Well, the way we do that is by standardization. What we do is we standardize this score of 67. Now when I standardize, I subtract the mean and divide by sigma. The mean of this distribution is 64.5, and then I'll divide by sigma, which is 2.5. So this distribution would be the probability that z is less than 2.5 divided by 2.5 is 1. So what happened here when I standardized, the value that I am looking for now is a z-score. So I've standardized this. So basically this is asking for me, what's the probability now, I don't have to say women's heights or anything else, what's the probability that an observation is less than one standard deviation above the mean? So less than would be this direction. And we already know something about this. 68% of the data lie within one standard deviation of the mean. So this value right here must be 34% because it's half of this distribution. And it's kind of like putting together pieces of a puzzle. Now this probability that z is less than 1 then is 0.5, because that's this area right here, plus 0.34 or 0.84. So this means about 84%. Okay, and again that second area came from this 34% right here. It's kind of like putting together pieces of a puzzle. We have to account for 100% of the area somehow. So given that we use that empirical rule, the percentage of women who are shorter than 67 inches should be about 84%. So again, that was using the empirical rule. We haven't used any tables yet. Now this standardization procedure, we're going to follow this. We're going to do this over and over again, and it's so important that we use the correct notation. So don't skip any steps here. Now the next thing we're going to look at is, what if we come up with a value that's not exactly one standard deviation or two standard deviations or three standard deviations? How would I work with that? And the way that we'll work with that is by using that table that I handed out to you. So go ahead and grab your table, and notice on your table, on one side of the table you have positive values that are running down the left-hand side of the table, and on the other side of the table you have negative values. So go ahead and grab out your table, make sure you flip it over to the side that has the negative values running down the left-hand side. So what we're looking at here is we're trying to find basically areas to the left. So this table gives us the area under the standard normal curve to the left of any z value. So if I were to sketch this curve, no matter what z value I chose, remember the mean is 0 here, this would give us the area to the left. So this would be some negative z value. Now if I use the opposite side of the table, if you flip your page over, it's going to give me the area to the left as well, but I'm starting with positive values. So they should be more than 1/2. So everything on this left-hand side, where the negatives are, these will always be between 0 and 50%. Okay, the other side will always be between 50 and almost 100%. So how do we use this table? Well, what we do is we talk about the z-score, and this is the number of standard deviations that your observation is above or below the mean. In this case, because it's negative, it's below the mean. So if we looked up a z-score of negative 2.50, I would go down to negative 2.5 and we'd go 0 over, notice the 0 here, and that would tell me that 0.0062 is the area to the left of 2.5 standard deviations below the mean. So the way that this would look is my mean is at 0, and I know it's at 0 because I'm using a z-score. Negative 2.5 is clear out here. and this means to the left right here. So this area is 0.0069. That's that area. Oh, I'm sorry, it's not 6.9, it's 6.2. Look at my table a little better. So 0.0062. Now over here, the negative 2.51 is talking about the area to the left. Now because I'm further out on my curve, I would expect that that area would be a little bit smaller, but not much. And it's 0.0060, so it is slightly smaller. So again, that's what this table is used for. Now clear over here at negative 2.56. Again, draw a picture every time for these. Here's my mean. Here's negative 2.56. I'm even further out on this curve. So I'd expect even smaller area, and I get 0.0052 for that value. So being able to use these normal tables is going to be very important. In the copy I gave you, write all over, do what you ever need to do with that one. I will always give you a clean copy for a test. So if you need to make notes on that table, go ahead and write on that. Now a lot of times we need to remember what's going on with these z-scores. This on the outside is the number of standard deviations I am above or below the mean. Everything on the inside of the table gives you the area to the left. It's giving us a probability, or if you want to think about multiplying by 100, it gives us a percentage as well. So like this value would be 7.78%. So once you know how to use your normal tables, things start to go a little bit better because we don't have to spend a lot of time calculating values. So let's go ahead and look at an example where we're using our normal tables again. So keep your normal tables out. So for this particular example, I'm looking at a z-score of 1. Well, what does a z-score of 1 mean? Well, that means I'm 1 standard deviation above the mean. And because it's the letter z, that means I'm at my standard normal random variable with a mean of 0 and a standard deviation of 1. So what ends up happening here, if I were to look one up inside my table, I'd go to 1.0, I get 0.8413 here, and that represents this entire area to the left. Now if you remember the example we did, we got about 84%. So scroll up in your notes and check it out. We got about 84% for that area, and we can see here that that's really close. So we're doing the same exact problem here, and we got about 84% last time. But when we use our exact normal tables, we find out that it's actually 84.13% after we standardize the score. Now because of symmetry, if 0.8413 lies to the left of 1, that must mean 0.1587 must lie to the right of 1, because the total area underneath this curve has to be 1. Now notice there's no area directly above the number 1. If we want to find probabilities associated with these, I have to have intervals. I have to have area to the right, area to the left, area between. But if I said what is the probability that x equals exactly 1 for a continuous distribution, that would equal 0, because there's no area above a single point on a curve. And this is important. It will definitely be some sort of a true-false question on a test. So definitely no, there's no area above a single point on a curve. Very important, and we'll revisit this in a little bit as well. Now again, this idea of symmetry becomes so important. So again, because of symmetry, I know that the total area underneath the curve is 1. So if I find the area to the left, let's say here, if I look up 2.33 in my table, and again that would be on the positive side of the curve. If I look up 2.33, I get 0.9901. The total area underneath the curve has to be 1. So to find this particular area, I would take 1 minus 0.9901, and that would give me this value right here. Now because of symmetry, the area to the right of 2.33 is the same as the area to the left of a negative 2.33. Now these are all probability statements. So this shaded area right here, this would be the probability statement that z was greater than 2.33. This would also be the probability statement that Z is greater than or equal to 2.33. Now the only difference here is here I have a greater than or equal to, here is greater. There's no area above a single point on a curve, so I don't need to worry about whether I have an equal sign or not here. For a discrete distribution, it was very important. For a continuous distribution, it doesn't end up being important at all. So again, if we're trying to find the area to the right of some value of Z, remember, I want to think about total area and then subtract out this region right here, and I'll be left with the area of interest. So again, it's like putting together the pieces of a puzzle and making everything fit. And the important part is that the total area under the curve always sums to 1. It's a symmetric distribution, so the area above a value to the right is the same as the area below the same value that's negated to the left. Let's go ahead and look at another example. We're going to use our tables again, so grab your tables. For this particular example, we are using our standard normal random variable again. So Z is distributed normal 0, 1, mean of 0, standard deviation of 1. And then what I want to do is I want to find this area between, this shaded area right here. Well, in order to do that, I'll find the area to the left of 2.2 and then subtract off the area to the left of 1.4. So the way that this probability statement reads is I'm interested in finding the area between 1.4 and 2.2. This notation, the two less than signs, mean between. Now remember, it doesn't matter if I have an equal sign here or not. So what I do then is I find the probability that Z is less than or equal to 2.2, and I subtract off the probability that Z is less than or equal to 1.4. Now grab your tables. If you look at the probability that Z is less than or equal to 2.2, you would get, let's see, 2.20, 0.9861. So this is equal to 0.9861. And then I subtract off the area to the left of 1.4, and if you grab your tables and look up 1.40, you get 0.9192. So to find that area of this shaded region, you would take 0.9861 and subtract off 0.9192, and you get 0.0669. 0.0669. But this is how the probability statements read, and I would really encourage you to use these probability statements instead of just kind of haphazardly writing stuff down. Now remember, we do not subtract the Z values, we subtract the probabilities. Now another quick thing we could note are some other notations. So we used a probability statement that Z was less than or equal to 2.2. Another way we can write that is phi of 2.2. That means if I look up 2.2 in the normal table, what do I get back? In this case, I get 0.9861. So a lot of times you'll see this notation as well, and no, that just means the area to the left of that point. It kind of has to do with cumulative probability, or adding up that area. So being able to find the area between values is very important as well. Let's go ahead and look at an example where we're standardizing scores again. So for this example, we're looking at the blood cholesterol levels of men aged 55 to 64, and they tell us that these levels are distributed approximately normal with a particular mean of 222 and a standard deviation of 37. So the first thing I would say here is I'm going to say cholesterol, UC, is distributed normal. And usually for approximately normal, sometimes I'll put a dot up above the tilde sign. So C is distributed approximately normal with a mean of 222 and a standard deviation of 37. The first question is, what percent of middle-aged men have cholesterol greater than 240? So what we could do to figure that out is we could look at our curve. So we could start with our curve, and we could start with our mean at 222, and then we could look at 240. Now it says, what percent of middle-aged men have high cholesterol? Greater than 240. Well, that's this shaded region right here. But I don't have a table that tells me about a distribution with a mean of 222 and a standard deviation of 37, so I have to standardize these scores. Okay, so the way this works is we would talk about the probability that cholesterol was greater than 240. I would standardize the mean. So when I standardize the mean, my variable becomes a z, and I take 240 minus 222 divided by 37. So in this case, I get the probability that z is greater than, and again, where did I get this? 240 minus 222 divided by 37. And make sure you're using your calculator carefully, and you're not just taking 222 divided by 37. So 240 minus 222 divided by 37, and I get 0.49. Now I will always round these to hundreds because that's what our tables are good for. So now when we look at this, what happened is our mean standardizes to 0, 240 standardizes to 0.49, and that says, oh, I'm 0.49 standard deviations above the mean. The score of 240 that was a cholesterol score standardizes to a z-score of 0.49. Now if I look at 0.49 on my tables, I get 0.6879. So I get 0.6879. And remember, that's the area to the left. Well, to figure out what the area to the right is, I take 1 minus 0.6879. And I get 0.3121. So my answer would be about 31%. So the answer here is about 31%. Now notice down here what we did is we had our score that was originally given for cholesterol level. Here's my standardized score. Here's the area to the left, here's the area to the right, so that's what this is referring to. Now again, I don't really encourage you to do too much rounding until you get to the very end of a problem. Now the next question is what percent have elevated cholesterol? Now elevated cholesterol is between 200 and 240 for our scores. So that one will look like cholesterol levels between 200 and 240. Now again, it doesn't matter if I have equal signs here or not. So what I want to do is I want to standardize these scores by subtracting the mean and dividing by the standard deviation. And again, C will standardize to Z, our standard normal random variable. 240 minus my mean divided by my standard deviation. And let's go ahead and look and see what I get for values here. So I take 200 minus 222, so I should get a negative number here because I'm below the mean. So I get a negative 22 divided by 37, and I get a negative 0.59. It's less than Z. Now we already standardized 240, so here we know we get 0.49. So I'm trying to find the area between negative 0.59 and 0.49. So this picture shows us one standard deviation. Let's go ahead and look at what else this picture shows. So let's say 200 is right here, and let's say 240 is somewhere right here. So what I'm trying to find is this area within 200 and 240 milligrams. Okay, so I'm looking for this area right here. Well, what I'll do is I'll find the area to the left of 240, which is to the left of 0.49 standard deviations. And then I'll subtract off the area that's to the left of 200 for my lower end of my cholesterol level. So the way that this will look for our probability tables is I'll have phi of 0.49 minus phi of negative 0.59. So if we look up 0.49 in our tables, I get 0.6879. And if I look up negative 0.59, and to look up negative 0.59, you're going to have to flip your tables over. So negative 0.59, I get 0.2776. And again, when I work with these, there's no need to round until the end. So up here, when they have these examples, they're kind of over rounding a little bit. You can round at the end. I get 0.4103. So this means 41%. So what percent have elevated cholesterol levels? 41% do based on this. And again, it's like pieces of a puzzle. There's a lot to keep track of there. So it's really important, again, that you draw a picture, and then once you have a nice picture drawn, shade in the areas that you're looking for, and of course that area is associated with probability. Now, we've used the normal tables one direction. Let's go ahead and work the normal tables backward, meaning given a percentage, where was the score that came from? So we're still using the normal tables, but instead of being given a standardized score to look up on the outside, we're given a probability or an area that we find on the inside and kind of work out from there. Now if you notice, not every single probability value is listed. For instance, 0.0042 isn't here. So if we wanted to work with that, what would we do? So we're going to have to kind of come up with some rules for that. So the inverse normal calculations are going to be used to work this table backward. Given a proportion or percentage, where did that score come from? So for instance, if I look up 0.0125, that means 1.25%. So the z value that's associated with that is negative 2.24. So the way this looks then, I'm working with z, our standard normal random variable, so the mean is 0. If I have 0.0125 to the left, the first thing I know is that area is very small, and since it's to the left, it has to be below the mean. So what I'm starting with is a picture like this, and then I'm saying, what is this? How many standard deviations do I have to be below the mean in order to make this happen? So since this is a probability or an area, I look inside the table, and come up with the closest I can get to it, which this one happens to be exact, and that's associated with negative 2.24. So this value is 2.24, and it's below the mean, so I need to make sure I have a negative value there. So being able to work the tables forward and backwards is very important, and we'll get lots of practice with that with quizzes. Okay, let's go ahead and look at another last example before we talk about quantile plots, or trying to determine whether a data set is normal. For this example, we're looking at the lengths of pregnancies, and in particular when we have malnourished mothers. And if they're given vitamins and better food, then we can talk about the length of the pregnancy. So I'm going to say L here for length of pregnancy is distributed approximately normal with a mean of 266 and a standard deviation of 15. It says, how long are the 75% longest pregnancies in this population? Well, if I have a mean of 266, 50% of the pregnancies will be more than 266, above 266. So if I want to find 75%, I know I'm going to have to go below the mean. Okay, so that tells me I'm going to shade in this particular region. So if I wanted to, I could look up 0.75 in my table, but remember, that's not going to be quite the right value because I'm looking for the area to the right, and the table gives us the area to the left. So the first thing that you could do is you could say phi of some number is going to be 0.25, because right away, because of symmetry and the fact that I know the total area underneath the curve is 1, the area to the left has to be 0.25. So we could look up some number and get 0.25. So grab your tables, and let's come up with the closest thing we can on the inside to 0.25. So let's search around here. 0.25. Looks like we can get pretty close. Oh, here's an exact value. It's at negative 1.96. Well, that's not right. That's 0.025. We want 0.25. So let's try and get a closer value. And again, it has to be 0.25. The closest value that we can come up with to 0.25 looks to be a negative 0.67. Notice 0.25 is not on the inside of the table. It's in between 0.2514 and 2483. 0.25 is the closest to 0.2514, so we'll use the normal value for that. So that's negative 0.67. So this implies this number that I don't know about is negative 0.67. So this means I'm 0.67 standard deviations below the mean. That's what this is meaning. So if I standardize this mean, I get 0. If I standardize this score right here, I get negative 0.67, and I want to work backward. So what we do is we take our standardization formula and we solve for x. So another way we could look at this is negative 0.67 equals x minus the mean of 266 divided by our standard deviation of 15. And then we solve for x. Now when we solve for x here, the first thing we would do is multiply through by 15. Whatever you do to one side, you do to the other. In this particular case, the 15s would cancel on the right. And then to work from here, I'd add the 266 across. So I'd get x equal 266 minus 0.67 times 15. And I get here 255.95. So again, take a minute to verify that. You're going to have to be using some algebra to figure these out. Yes, we get 255.95. So that's what we're saying here. We're saying that this value is 255.95. And that is below the mean of 266, so that makes sense. So we have the area. What we want to do is work backward. So what we can conclude then is the 75% longest pregnancies in this population are 255.95, or about 256 days or longer. So again, working forward and backward with the normal table is going to be very important. Okay, the last thing we need to talk about are normal quantile plots. Normal quantile plots basically will give you the information about whether your data is normally distributed. Because a lot of times we don't know the shape of the data. What we typically would do is produce a histogram and then try and model the data or draw a smooth curve over the top of that. But a normal quantile plot gives us that information really quickly. Now with the normal quantile plot, and we're not going to be producing those, but we will be interpreting them, it's hard to judge a curve and say yes, that's normal, or no, that's not normal. But it's really easy to see if something follows a straight line. So the math behind a normal quantile plot basically takes each data point and it transforms it to a different scale and a comparison point, and then based on that comparison point I can just look at it as a straight line, and if it's a straight line, it's normal. If it's not a straight line, it's not normal. So for a normal quantile plot, what we need to do here is we need to think we're looking for a straight line pattern. If we have a straight line pattern, that implies that we have normality. Now even if it's only slightly straight or mostly straight, we still have some sense of normality there. So let's go ahead and look at an example. Now the normal quantile plot on the left, when we view this, we can see that's very close to a perfectly straight line. So this is telling us that we have normal data, approximately normal data. Now if we look at this graph, a straight line doesn't do a very good job at all talking about it. So I would say that this is not normal, not normal. Now in terms of skew, I wouldn't necessarily be able to talk about skew on an exam. What I would want you to get out of this is the left curve, because I'm looking at the quantile plot, the data is normally distributed. The right curve, because I'm looking at the quantile plot, is saying, you know what, the data is not normally distributed. Now, why is it right skew? But again, this is not a talent that I would expect you to have. I just want you to be able to identify things that are normal or not normal. But for the right skew, most of the data points are short survival times, while a few of them are longer survival times. And so that kind of gives me the idea these longer survival times would give me this right skew type of shape. So I had data like this. I did the normal quantile plot, and you can do those in Minitab if you want. The normal quantile plot would produce this to indicate, you know what, this data is not normally distributed. Now being able to use these tables is so important. We're going to be using these tables continuously for the rest of the semester. So we are going to be looking at some worksheets, some quizzes to make sure we know how to use the tables, and then we're going to eventually get past this to be looking at some problems where we can apply this information to find probabilities, percentages, and proportions that we're interested in determining about different populations.